Okay, so today we're going to begin on page 428, and when you look at the top of page 429, like top of page 428 says organic chemistry, the top of page 429 says aldehydes and ketones. Okay, you might say, well, that doesn't make any sense. We're going backwards. Okay, I would agree. Okay, but in this case, okay, one of the things that it doesn't say on our schedule over there, but I think I just mentioned it just briefly, just once, and that was the very last thing that we talk about in with the organic section, is what we call acetal, hemiacetal formation and acetal. That's the last of the reactions that we do until we get to that of the lipids. Well, I guess there's maybe a little bit you could say with that of the carbohydrates. With the proteins, it's just memorizing the associated amino acid structure. Okay, so we're looking on page 428 where it says hemiacetal and acetal formation by reaction with alcohol. Okay, aldehydes and ketones react with alcohols to form hemiacetals and acetals. Hemiacetals and acetals are they are important structures in carbohydrates. So that's why I think it's important to reserve that till the very last thing that we talk about with this section before we move on to the biochemistry, which is carbohydrate structure. Okay, so the reaction of aldehyde and ketones with alcohols requires an acid catalyst and takes place in two-step process. First, the alcohol adds to the carbonyl group. So even if we didn't go any further, what does that mean to you, a carbonyl group? Yeah, it's going to be a double bond oxygen. It doesn't make reference if it's a ketone, aldehyde, acid, ester, any one of those. It's just saying a carbonyl group to form a hemiacetal. Second, if excess, the alcohol is present, the hemiacetal reacts with a second molecule of alcohol to form an acetal. The second step is dehydration reaction, similar to the intermolecular dehydration of alcohols to form ethers. The reaction is illustrated for propanol and methanol. Okay? So, remember when we always made reference to this, all these reactions, it's all about the water. And whether we're taking what appears water from different compounds, in this case it's alcohol, but not for the reasons that you might think. Okay, so they choose per se propanol, but we'll do something a little different. No, not they say propanol. Okay, we're going to use ethanol instead. Okay, so you have that example in your book, and then you also have the opportunity to visualize this reaction as it takes place. So if a word problem was to state form a hemiacetal structure from ethanol, okay? So once you see that term ethanol, what would that mean to you? It's got to mean two things specifically: what the structure looks like and what the organic family is. So ethanol, what does that mean to you? Okay, so two carbons, correctly said. Okay, and then I think to me it just makes more sense, well, either left or right. Okay, so there's our ethanol. Then we're going to add an alcohol to that. And I would like to think I could get this color coordinating right, but by the time I do that, I'm probably going to make a mistake on that, and it's going to be irritating. But we'll give it a try. Hey, I'm actually able to, maybe I let that lotion sink in or absorb quick enough, or maybe I didn't put an overabundance amount on. Okay, so we'll do this. Try to do this without looking. So we're talking about methanol now, which means what type of organic compound is that? One carbon and Yep, so yeah, hydroxyl group or an alcohol, okay? So then what we would do here, okay, we'll do that, and then no, I don't think, that's not how, we'll do a molecular formula instead. So that's a clue right there, okay? Which looks kind of silly when you visualize that, because if we were going to do the structural formula, okay, this, we would all agree that's what methanol is. So that's where I have failed you, okay? See, it's so tricky trying to visualize what the molecular formula should be and when you actually have the structural formula. Okay, so now, whether you have this bond in here or not, it's probably really not that important, okay? Because, well, we know that that's going to be a single bond between these two. And the reason that we've got this color-coded now, okay, is that it said we needed a catalyst. That, when it says, anytime it says H+, that's going to mean an acid catalyst. Typically, it's probably sulfuric. Aldehyde alcohols requires an acid catalyst, okay? So, it doesn't say how strong. So, we're just going to, we know it just has to be an acid catalyst. So, for our purposes here, we'll just keep things consistent and just say that, okay? There's our acid catalyst, sulfuric acid. Okay? Because these travel in a very similar nature, like intramolecular dehydration, which we know is going to be from that sulfuric acid. And here is why we want this color-coded. And I don't know if you're going to be able to see this on film. I'll get out of the way. It looks like we should. I don't know what this looks like if you go back and watch it, but we've got these letters are written in black, and this hydrogen is in purple, okay? So what we see happening then is this will proceed to this side, okay? So here is our two carbons, okay? And then, remember, there's nothing down there. We've got that hydrogen. So what's going to happen is that double bond is going to break. So we're going to put that oxygen up here, okay? And then there's a reason why that hydrogen is in purple. When this breaks, it gets reduced. And that's what a lot of those reactions did with aldehydes and ketones being reduced to primary alcohols and secondary alcohols. This is something very similar, okay? But rather reducing it, it's being dehydrated, okay? So now we take that hydrogen and put that up here, and then notice that once we take this double bond off, what's the problem with that second carbon over there? It's not that it's a problem, but well, it just needs more, maybe not hydrogen, but just a bond, okay? So what we see left from the rest of this, okay, and we would just attach that to the bottom here, okay? And perhaps it makes more sense if I would have started here. Remember, we said it's probably not that big of a deal. We'll just put this O here, and then, of course, we know that that hydrogen is attached. Okay. Oh, now my hands are getting slippery. There. Okay. So now we've formed what we would consider being a hemiacetal structure then. Okay. So should this methanol be in excess, okay, and we've seen a couple problems like that. And what we mean by that is when alkynes react with, okay, I got to think about this. Could be with an asymmetrical reagent in excess, from an alkyne to an alkene, all the way down to an alkene. Because one of the things that we would write here is that catalyst is in excess. So, not the catalyst, yeah, not the catalyst here, but what we're reacting it with. If that's in excess, then notice what does this section have to deal with? Hemiacetals and acetals, okay? So what that means then is we can look at this one more time and use our same logic, okay? And we say it's all about the water again. I don't know if I'm comfortable enough to say, I can't stress that enough, but because the last thing we want you to do is, where did you learn this from? If that's what a professor says in that tone, we went to Flandreau or something like that. But if, wow, this is good stuff. Yeah, we did that with Coleman Egan. Did I turn this on? Yes, I did. Okay. So if this is in excess, okay, and you say it's all about the water, what would this have in common on this compound when we say it's all about the water? What are we going to strip off of there? Water. So what is this going to grab from that compound, do you think? Right, because when we say a hemiacetal structure, it's this. It's just half of this molecule on here is a hemiacetal. If this is going to become a full acetal, this is in excess. So then this has to be in black now. Okay, so that gets stripped off of there. Okay, and then now you've got a full acetal structure, okay? And you would have to be told that because what it says here, okay, the reaction proceeds the reaction proceeds in a similar manner for ketones. The products that formed from ketones were formerly called, oh, we don't do that, okay. Where did I see that? Oh, it was above there, okay? Second, if excess alcohol is present, the hemiacetal reacts with a second molecule of alcohol to form an acetal, okay? So if a problem was to say form a hemiacetal structure, well then it's just here on the bottom. If it forms a full acetal, then you have a mirror image of each other. And that's what that's referring to, okay? We're not going to go into these hemiketals or maybe that's the name how it's pronounced. It might be kettles, but I would guess it's probably ketals. We're just not going to do that. We're just more concerned from aldehydes. All right. That was a lot of information in a short amount of time. Are we good with this? Okay, so I see a yes on the bus, Okay. All right. So as far as your problem quiz is concerned, okay, remember there's 4 types of reactions that we talked about, okay? There are, I don't want to say saponification. That's an acid with a strong base. Then we had esterification, an acid and an alcohol. Then we had water hydrolysis, okay? That means you're taking an ester and breaking it apart due to water synthesis. then the fourth type is what we just discussed here. Yes. You can do it! What's an inspirational chant that we can, is that a good one? You can do it! I can't, what would be a better one? Oh, I was going to say you got 2 minutes.
Oh, okay.
No, Google is not the answer. Okay. Otherwise, if there's nothing else, at least we're not going to spend a lot of time on these hemiacetals. Are we going to do hemiketals? Not for tomorrow, okay? And I don't think we do that on your exam either, which will be at some point next week. Vocabulary evaluation of some sort, probably on the 30th and or Tuesday. Then we can review again on Wednesday, the 31st, and then 2-part exam on February 1 and February 2. And then once February 5th hits, we'll be into the biochemistry. That's approximately where we're at and where we're going. Okay. Is there something that you may like to ask that someone else might think is beneficial, or for our other students?
Some of the reactions that will be on it tomorrow.
Sure. I'll just go ahead and hit pause here for a moment. Okay, I was going to erase that, but I thought, well, no, we can certainly leave that up here. But to me, this is probably one of your more difficult problems because, yes, there's naming on there, and that's why we want to go over this as far as a review and naming them. Because if we are saying create propyl 2-methyl ethanoate, the first thing I think that would make the most sense is draw out your ester first. So in order to do that, oh, this coffee's strong. I knew I took that too early, but once the second batch goes around, I put a little more water in there. It won't be quite as strong. Okay, so we need to draw this ester here. So when we look at that, what looks like the parent chain, there's going to be 6 total carbons, but that's not the part that we consider the parent chain. Does anyone think they might know why? So if we're going to draw out our ester first, and I think that's the best way to approach this, is once you see what your ester is, well then, okay, now we can proceed on how to create it. So what would this propyl mean to you then? Okay, so we'll start with that, 3 carbons. Okay. And then after those 3 carbons, what's this telling you here? Okay, so in this case, it doesn't even matter if we say start on the left or the right side, but if this said butyl 2-methyl ethanoate, then it's going to make a difference, because we established once you make these esters, okay, we say start from the center and work out, okay? But since this is an odd number, it doesn't matter if we started here or if we started here. But if this was going to say butyl 2-methyl ethanoate, well then that would make a difference, okay? It would go on this carbon, not that one. Why would that be though? Yeah, because your oxygen's over here, and you need to start on that carbon, not this one. Okay, but we don't have that, so we're just going to go ahead and do this. So then on our second carbon, is that missing a dash there? We're going to put a methyl group, doesn't matter, top or bottom. Okay, so we've established which side, the alcohol or the acid side. We've done the alcohol side because this is referring to the acid side now, which is how many carbons? Okay, now I can see this happening too. It would be a very simple mistake to make, okay? And that would be doing this. But we know that that can't be right, okay? Why do we know that that is not right? Because what does the organic family of an ester have to look like? Yes, it has to be next to this carbon. It can't be on that one. It's got to be here. And, oh. It was, where's my eraser? Okay. So now we've got our ester. It says create propyl 2-methyl ethanoate. So you've already correctly established that we know this is your alcohol side, this is your acid side. Then once you have that, okay, it's not that you're home free, but you've just made things a heck of a lot easier for yourself. Because we know that when we're doing esterification, we know we have to have an alcohol and we have to have an acid. So we've got our alcohol side, which means, what alcohol are we starting with? Propanol. And can we be even, no, we can't be more specific. I was going to say isopropyl alcohol, but that's not correct. So here is our propanol right now. Then what do we have on this guy? Yep, there's our methyl group. Methyl. There's our methyl group. So then we just have to put our acid on there, which would be 2 carbons. Now, could you do that? Yes? No? Sure, that's ethanoic acid. But why might it be easier to switch them around? Right, because this is where they combine. It would make it a lot easier to put that double bond oxygen over here rather than on the right carbon. Well, I guess you are putting it on the right carbon. Yeah, okay. I'll stop now. Yeah, make sure you put it on the right carbon. Okay. Sorry, I had a meeting last night that lasted a little longer than I thought. But see, it is, I'm sure he would think that's hilarious. Yeah, blame me. Yeah, blame me.
Oh, yeah, you'd think it's funny.
Yeah, I think he would too. Yeah. All right. So then, now that we've got that done, now we can proceed. You have created, well, the only thing you're missing is the same thing up there, and you have to have an acid catalyst to do that. Now you have correctly created your propyl 2-methyl propyl 2-methyl ethanoate. Yeah. Now you've done that. Okay. But what will work best in I think the directions state this, okay? You can get this correct, but for the wrong reasons, okay? this is what we mean. You could, you could do this and say, we know that we're going to strip water off of there. There's our water, and it's gone. No one can argue or dispute that. But is there a problem with that? And maybe we haven't spent enough time on that, but for the same reason we call this the alcohol side, okay? That's not how the two compounds come together. It has to be this, the hydrogen on this, and then the entire OH on that, okay? So yes, if we had it how we did before, you get it right, but it's for the wrong reasons, okay? We want you to get it right for the right reasons. Okay, so to me, we're illustrating two things at the same time. This is esterification, and if we add water to our ester, that's water synthesis, so what direction is that reaction going? And break, isn't that break? No, that's the moonwalk. Oh, well, they can't see my feet doing the moonwalk. Sure, we'll go with that. All right, so this has two reactions. Here's the third one, and then probably the simplest, well, I think so, and it's been the longest that we've talked about, your saponification or forming soaps, which means, well, not forming soaps, it's just saponification. You have an acid and you react that with a very strong something. There are 4 of them on a baseball or softball field. Yeah, see? Yeah. But although I've never, home plate, yes, I always just say home plate. I suppose it's a base, yeah, you can have a force out there, yeah. But yeah, an acid with a strong base forms a carboxylate salt. Those are your 4 reactions. Okay. Anything else? Front row.
So
Good.
like a question like that, okay with us just starting with just the one reaction? You don't want us to like make the acid and make the alcohol? Just start with
Oh yes, you would start with, but to me, you could if you have a really good understanding, you could do this. Yes, that's true. But to me, it makes most sense to write down what you're actually forming. Then you can see the
Right.
parts. Okay. But yeah, you could start with that.
I just mean like do you want us to just start with like ethane and then make it into an acid?
Oh no. We're not doing that. No. I never thought of that. Yeah, what are you doing?
Like I just like when he said just create that, I figured he wanted to like start from nothing.
Oh, well, yeah, that's a good question. I never thought of that, but no, we're not doing that. Front row, we're good.
Number 4, what is the parent chain on the alcohol side? Just start with derivatives and give them out.
Oh, we said we're going to come back to that, didn't we? Okay. So to me, number 4, we're going to do this. We're gonna do this. It's still gonna be a butyl group. And then instead of 4, 4, we're gonna do this. I think we've done something very similar. I think that's what we want to do for number 4. Okay? I think that's what would make the most sense.
And this last question, you just want us to do one with sodium hydroxide and one with potassium hydroxide?
Yep, that would be
Okay.
the 2 ways. Yep. All right. So that's all I have. So we'll work on get that wrapped up tomorrow and the chapter wrapped up next week. Then we'll get on to the carbohydrates. Catch up to you next time.